Look up. On a clear, moonless night, far from the glare of city lights, the sky reveals its true and terrifying majesty. A velvet darkness is punctured by 1,000 pinpricks of ancient light, each one a distant sun, a beacon across an unimaginable gulf. Humanity has gazed upon this celestial canvas for its entire existence. We have charted it, named its constellations after our gods and heroes, and woven its rhythms into the very fabric of our earliest calendars. Yet, for all our staring, for all our dreaming, we have only just begun to grasp the sheer, soul-crushing scale of it all. Our minds are not built for this. They are calibrated for the familiar scales of our own world. We understand the height of a tree, the breadth of a river, the distance to the horizon on a flat plain. These are human measurements, born of an existence tethered to the surface of a single, tiny, fragile world. To embark on a journey through the true scale of the universe is to agree to abandon these comfortable anchors. It is a voyage that requires a radical recalibration of the self, a willingness to feel profoundly, utterly small. Our journey begins here, with you, with the 1.5 to 2 meters of bone and flesh that constitutes a human being. This is our fundamental unit of perception. From this vantage point, a mountain is colossal. Mount Everest, stretching nearly 9 kilometers into the thin, cold air, represents the very limit of terrestrial grandeur. It is a monumental challenge, a feature so immense, it has shaped cultures and claimed lives. But in the cosmic scheme, this geological titan is less than a microscopic bump on the surface of our planetary home. Let us pull back from our individual perspective. We rise above the continents, watching cities transform into grids of light, mountain ranges crumpling into textures on a vast mottled sphere. This is Earth, our world, a globe with a diameter of nearly 13,000 kilometers. To circumnavigate it, even in a modern jet, is a multi-day endeavor. The ancient Greeks, with their brilliant geometry, were the first to truly measure it. Eratosthenes, in the 3rd century BC, using nothing more than wells, sticks, and the sun, calculated our planet's circumference with astonishing accuracy. It was a monumental intellectual leap, the first step in placing a number on the dimensions of our reality. For the first time, our world was not an endless, flat expanse, but a finite, measurable object adrift in a greater void. For millennia, this sphere was our entire universe. The sun, the moon, the planets, and the distant stars were thought to be small lights affixed to crystalline spheres rotating just beyond our atmosphere. It was a cozy, human-centric model, but our journey must take us beyond this ancient cradle. Our first destination is our constant celestial companion, the moon. It hangs in our sky, a familiar silver disk. Its gravitational pull tugs on our oceans, creating the tides. Its phases have guided farmers and poets for ages. It feels close, almost within reach. The reality is quite different. The average distance to the moon is 384,400 kilometers. This number is so large it's almost meaningless. Let's try to visualize it. If you were to drive a car at a constant highway speed, without stopping for fuel, food, or rest, the journey would take about 6 months. The Apollo astronauts, propelled by the most powerful rockets ever built by humanity, took 3 days to cross this chasm. This distance is so significant that it introduces a new concept, the speed of light. Light, the fastest thing in the entire cosmos, takes 1.3 seconds to travel from the moon to Earth. When you look at the moon, you are not seeing it as it is, but as it was 1.3 seconds ago. This is our first encounter with a fundamental truth of cosmology. Looking out into space is to look back into time, and this is just the first, smallest step. Now, we turn our attention to the heart of our solar system, the source of all our light and warmth. The Sunday, from our terrestrial viewpoint, it's a blindingly bright disk, similar in apparent size to the moon. This is a grand illusion, a trick of perspective. The sun is about 400 times farther away than the moon, and it is also, by cosmic coincidence, about 400 times larger in diameter. This is why they appear to be the same size in our sky, a fluke that allows for the spectacle of a perfect solar eclipse. To comprehend the Sun's true immensity is another challenge for our minds. Its diameter is 1,4 million kilometers. You could line up 109 Earths side by side to span its width. If you were to imagine the Earth as a small marble, the Sun would be a colossal, glowing sphere 1.5 meters across. Its volume is so stupendous that you could fit one. 3 million planets the size of Earth inside of it, with room to spare. It is a thermonuclear furnace of unimaginable power, fusing hundreds of millions of tons of hydrogen into helium every single second. The energy unleashed by this process has powered life on our world for billions of years. The distance to this stellar engine is the next rung on our cosmic ladder. It is nearly 150 million kilometers away. This distance is so fundamental to our understanding of the solar system that astronomers have given it its own name, 1 astronomical unit, or AU. Light itself takes 8.5 minutes to traverse this expanse. The sunlight warming your face right now began its journey before you started your current thought. The star you see in the sky is always in the past. If the sun were to suddenly vanish, we on Earth would remain in blissful ignorance for 8.5 minutes, continuing to orbit a phantom star before our world was plunged into eternal darkness and cold. Our solar system is not just the sun and the Earth. It is a vast and sprawling family of planets, moons, asteroids and comets, all bound by the sun's immense gravity. And the defining characteristic of this system is not its objects, but its emptiness. From the sun, we travel outwards past the rocky inner worlds of Mercury, Venus, and Mars. Then we cross a vast belt of shattered rock and debris, the asteroid belt, a testament to a planet that never formed. Beyond this lies the realm of the gas giants. Jupiter, a failed star in its own right, is so enormous that all the other planets in the solar system could fit comfortably inside it. Its great red spot is a storm that has raged for centuries, a storm larger than our entire planet. Even further out orbits Saturn, with its breathtakingly intricate rings of ice and dust. Then come the ice giants, Uranus and Neptune, cold, blue worlds in the deep twilight of the solar system. To travel to Neptune, the outermost major planet, is a journey of 4.5 billion kilometers, or 30 AU. The Voyager 2 spacecraft, one of the fastest objects ever launched by humanity, took 12 years to reach it. The light from our sun, even traveling at its ultimate speed, takes over 4 hours to arrive there. From the surface of one of Neptune's moons, the sun would appear as nothing more than an intensely brilliant star, its warmth barely discernible. This is the scale of our own celestial backyard, a domain so vast that our fastest probes take decades to traverse it. The Voyager 1 probe, launched in 1977, finally crossed what is considered the edge of the solar system, the heliopause, in 2012. It took 35 years, and yet, on our journey to understand the true scale of the universe, we have not even taken the first real step. We are still standing on the doorstep of our own home. To venture further, we need a new unit of measurement. Kilometers and astronomical units become comically inadequate. We must now speak in terms of the light year. This is not a measure of time, but of distance. It is the distance that a beam of light travels in a single terrestrial year. Given that light moves at approximately 300,000 kilometers per second, a light year is a mind-numbing 9.5 trillion kilometers. It is a number so vast, so divorced from any human experience, that it can only be understood through analogy. Imagine our entire solar system, out to the orbit of Neptune, has been shrunk down to the size of a quarter, a small coin you can hold in your palm. On this scale, how far away is the next star? The closest star system to our own is Alpha Centauri, a triple star system. One of its members, a small red dwarf named Proxima Centauri, is our nearest stellar neighbor. On the scale where our solar system is a coin, Proxima Centauri is not a few feet away. It is not across the room, or even down the street. It is another coin located about 2 football fields away, and in the immense empty space between those 2 coins, there is almost nothing. Just a few stray atoms per cubic meter, a vacuum more perfect than anything we can create on Earth. This is the nature of interstellar space. Proxima Centauri is 4.2 light-years away. Its light, the light we see through our telescopes, began its journey to Earth more than 4 years ago. When we observe it, we are seeing it as it was during a previous administration, a different season of your life. To travel there with our current technology, like the Voyager probes, would take approximately 75,000 years, 75 millennia of travel through a cold, dark, silent void. This is the gulf that separates us from just the very next star. But let's not stop there. Our journey must press onward, into the galaxy we call home, the Milky Way. The faint, hazy band of light that we see stretching across the night sky is not a cloud of gas. It is the combined, unresolved light of billions upon billions of distant suns. We are looking into the dense, flat plane of our own galaxy from our position within it. Our solar system resides in a relatively quiet, suburban spiral arm, about 2/3 of the way out from the galactic center. This structure, our home galaxy, is a staggering piece of cosmic architecture. It is a barred spiral galaxy, a colossal, rotating disk of stars, gas, and dust. Its diameter is estimated to be at least 100,000 light-years across. Let's return to our analogy. If our entire solar system is a single coin, our galaxy, the Milky Way, is a sprawling continent the size of North America, a disk of stars 100,000 light-years wide. Our Sun is just one of an estimated 200 to 400 billion stars in this cosmic metropolis. That is more stars in our galaxy alone than there are grains of sand on all the beaches of Earth. Think about that. Pick a star, any star, in the night sky. The light from it may have left its surface when the Roman Empire was at its height. Light from the other side of our galaxy began its journey towards us when early humans were first learning to master fire. At the heart of this swirling vortex lies a monster, a supermassive black hole named Sagittarius A star. It has a mass equivalent to 4 million of our suns, crushed into a point of infinite density. Its gravitational influence orchestrates the dance of the inner stars, a silent, invisible puppeteer at the center of our galactic home. We orbit this center once every 230 million years. The last time our solar system was in this position in its galactic journey, dinosaurs were just beginning to walk the Earth. Our planet has made this circuit less than 20 times since it was formed. For centuries, we believed this galaxy was the entirety of the universe. All the stars, all the faint smudges of light, or nebulae, seen through telescopes, were thought to be contained within this single, grand island of stars. It was another comfortable, if vastly expanded, worldview. This notion was shattered in the 1920s, a moment of discovery as profound as Copernicus realizing the Earth was not the center of all things. The astronomer Edwin Hubble, using the powerful new Hooker telescope on Mount Wilson in California, was studying one of these faint smudges, the Andromeda Nebula. Night after painstaking night, he captured photographic plates of this celestial object. He was searching for a specific type of star known as a Cepheid variable. The genius of these stars, discovered by Henrietta Leavitt, is that their brightness flickers at a rate directly related to their true, intrinsic luminosity. They are cosmic standard candles. By measuring how fast one pulses, you can know how bright it truly is. And by comparing its true brightness to how dim it appears from Earth, you can calculate its distance with incredible precision. Hubble found a Cepheid variable within the Andromeda Nebula. He did the calculations, checking and rechecking his work in the cold mountain air. The result was unambiguous and earth-shattering. The distance to this star was over 900,000 light-years. He later refined this to be even further. We now know it is 2.5 million light-years away. This was a distance far, far greater than the known size of the Milky Way. The Andromeda Nebula was not a cloud of gas within our galaxy. It was another galaxy entirely, an island universe just as vast and magnificent as our own, separated from us by a chasm of intergalactic space that beggared belief. In that single moment of calculation, the known universe expanded by an unimaginable factor. Our one great city of stars was revealed to be just one of many. The cosmos was suddenly filled with countless other galaxies, each one a collection of billions or even hundreds of billions of suns, each potentially with its own planets, its own solar systems. The Andromeda Galaxy is our closest major galactic neighbor. It is so far away that the light we see from it tonight began its journey towards us 2.5 million years ago. When that light left its source, our own species, Homo sapiens, did not yet exist. Our distant hominid ancestors were walking the plains of Africa. That ancient light has been traveling across the void ever since, arriving now to be captured by our eyes and our telescopes. Andromeda is visible to the naked eye as a faint, blurry patch of light. When you see it, you are looking at the most distant object you will ever perceive, without optical aid, and you are looking millions of years into the past. This is the next scale of reality, the intergalactic. Our Milky Way and Andromeda are the two largest members of a small cluster of galaxies, known as the Local Group. This group contains about 50 galaxies, most of them small dwarf galaxies, all bound together by their mutual gravitational attraction. This cosmic family spans a region of space about 10 million light-years across, and even now, Andromeda and the Milky Way are hurtling towards each other at a speed of over 400,000 kilometers per hour. They are destined to collide in about 4.5 billion years. It will not be a cataclysm of crashing stars. Space is too empty for that. Instead, it will be a slow, majestic, gravitational dance, the two great spirals merging over hundreds of millions of years to form a new, even larger elliptical galaxy, which some have nicknamed Milkomeda. Our distant descendants, should they exist, will witness a night sky filled with a spectacular burst of star formation. But even this local group, this neighborhood of galaxies, is just an insignificant speck. As we pull our perspective back even further, we see that galaxies are not distributed randomly throughout the cosmos. They are organized. Our local group is on the outer fringe of a much larger collection of galaxies, the Virgo supercluster. This colossal structure contains over 100 galactic groups and clusters, and its total mass is over a quadrillion times that of our Sunday. It stretches for 110 million light-years. To cross it, even at the speed of light, would take 110 million years, and this is where our journey reveals the true, grand architecture of the universe. As we zoom out from the Virgo supercluster, we discover it is just one lobe of an even more gargantuan structure, our home supercluster, which astronomers have named Laniakea, a Hawaiian term, meaning immeasurable heaven. Laniakea contains roughly 100,000 galaxies, all flowing and moving together through space, drawn towards a central point, called the Great Attractor. This cosmic supercontinent is 520 million light-years in diameter. Now, at last, we can perceive the largest known structure in the entire cosmos, the cosmic web. On scales of hundreds of millions of light-years, the universe resembles a gigantic, three-dimensional sponge or a vast neural network. There are long, brilliant filaments, composed of superclusters of galaxies, glowing threads stretching across the void. Where these filaments intersect, we find the most massive galaxy clusters, the great cosmic cities, and in between these glowing structures are the great voids. Immense, nearly empty bubbles of darkness, some of them hundreds of millions of light-years across. These are the deserts of the universe, regions where galaxies are incredibly scarce. Our galaxy, our supercluster, our entire cosmic neighborhood, is just one part of one filament in this incomprehensibly vast web. This cosmic web is the skeleton of the universe, and its architects are mysterious and invisible. The glowing galaxies we see make up only 5% of the total mass and energy of the cosmos. About 27% is a mysterious, unseen substance called dark matter. We cannot see it, we cannot detect it directly, but we can witness its gravitational effects. It is the invisible scaffolding upon which the cosmic web is built, the gravity that holds galaxies and clusters together. The remaining 68% of the universe is even more baffling. It is a force known as dark energy. This is a repulsive force, a kind of anti-gravity embedded in the fabric of space-time itself. It is causing the expansion of the universe not just to continue, but to accelerate. The great voids are getting larger, pushing the filaments and superclusters further and further apart from one another. The true scale of the universe is not just spatial, but temporal and dynamic, shaped by forces we are only just beginning to identify. So, how far can we go? What is the ultimate limit? Our journey must eventually end at the boundary of what we can see. This is the edge of the observable universe. It is not a physical wall or an edge to space. It is a temporal horizon. The universe is approximately 13.8 billion years old. Therefore, the absolute furthest we can possibly see is the distance light has been able to travel in 13.8 billion years. This creates a sphere of observation around us, with Earth at its center. The radius of this sphere is about 46.5 billion light-years in every direction. You might wonder why it's not simply 13.8 billion light-years. This is because the space through which that ancient light has been traveling has itself been expanding the entire time. The object that emitted the light 13.8 billion years ago is now much, much farther away. The diameter of the observable universe is therefore about 93 billion light-years. Within this sphere, astronomers estimate there are at least 2 trillion galaxies. 2 trillion, each with hundreds of billions of stars. The number is so large it ceases to have any meaning. It is a statistic that numbs the mind. Every single one of those 2 trillion galaxies is a Milky Way, an Andromeda, a vast island of light and matter. And beyond that edge, beyond the oldest light we can possibly detect, we simply do not know. The universe beyond our observable bubble is almost certainly much, much larger. It could be hundreds of billions of light years across, or it could be truly infinite. We have no way of knowing. We are like sailors on a small raft in the middle of an infinite ocean, only able to see to our own horizon. The faintest, oldest light we can detect is not from the first stars or galaxies. It is a faint, uniform glow of microwave radiation that permeates all of space in every direction we look. It is the cosmic microwave background radiation. This is the afterglow of the Big Bang itself. It is a picture of the universe when it was only 380,000 years old. A time before any stars or galaxies had formed, when the entire cosmos was just a hot, dense, opaque fog of primordial plasma. As the universe expanded and cooled, this fog finally cleared, releasing this radiation to travel freely through space for the next 13.8 billion years, eventually to be detected by our radio telescopes. When we map this ancient light, we are looking at the very seed of creation, the faint temperature fluctuations that would, over eons, gravitationally collapse to form all the magnificent structures we see today. The cosmic web, the galaxies, the stars, the planets, and us. And so, our journey brings us back through the cosmic web, past the countless superclusters, back into our own Laniakea, and to the Virgo cluster. Back to our tiny local group, and towards the familiar spiral of the Milky Way. We fly through its outer arms, past billions of suns, and find our way back to one unremarkable yellow dwarf star. We pass the orbits of Neptune and Jupiter and Mars, and we see a small, blue and white marble shimmering in the sunlight. The astronomer Carl Sagan, upon seeing a photograph of Earth taken by Voyager 1 from 6 billion kilometers away, called it the pale blue dot. From that distance, our world was a single pixel of light, a mote of dust, suspended in a sunbeam. He wrote, "On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hero and coward, every creator and destroyer of civilization, lived there on a speck of dust, suspended in a sunbeam. This is the ultimate lesson of our journey through scale. It is a dual lesson of profound humility and immense preciousness. In the face of these cosmic voids and galactic multitudes, our principles, our conflicts, our perceived self-importance can seem to vanish. We are a fleeting, localized phenomenon on a tiny stage in a vast cosmic arena, and yet this tiny stage is everything we have. This pale blue dot is the only home we have ever known. It is a world teeming with life, with consciousness, with art, with love, with questions. We are, as far as we know, the only beings in this immense universe. Who can undertake this journey? Who can look up at the night sky and wonder about its scale and our place within it? We are a way for the cosmos to know itself. The iron in our blood, the calcium in our bones, the carbon in our DNA were all forged in the hearts of dying stars billions of years ago. We are literally made of stardust, and for a brief, flickering moment in cosmic time, that stardust has woken up. It has assembled itself into beings who can build telescopes, formulate theories, and attempt to comprehend the staggering, beautiful, and terrifying reality of the universe they inhabit. The journey is far from over. Our map of the cosmos is still mostly blank, but the quest, the innate human drive to look up, to measure, to understand, will continue. And with every new discovery, our universe will grow larger, and the miracle of our own conscious existence on this small, fragile world will only become more profound. Is it possible that the greatest mistake in the history of science is also its most profound and terrifying truth? It's a contradiction born not in a laboratory, but in the silent, unforgiving emptiness between the stars. For generations we have looked out into that perfect blackness and seen an absence, a cosmic canvas of serene nothingness, upon which the grand spectacle of galaxies is painted. We call it the void, the vacuum, the great chasm of interstellar space. It is the ultimate symbol of emptiness, a state so devoid of substance that it defines our very concept of zero. And yet, if the strange and bewildering laws of quantum mechanics are to be believed, this perception is not just wrong, it is perhaps the most profound illusion we have ever held about the nature of reality. We float now in your mind's eye, far from the comforting blues and whites of Earth. We leave behind the sun a fading spark in an ocean of ink and drift into the interstellar medium, the space between the suns. The silence here is absolute, a pressure so complete it feels less like an absence of sound and more like a physical presence. There is no air to carry a whisper, no medium to transmit a vibration. The cold is a primal force, a temperature just shy of the theoretical limit, the absolute zero, where all motion is thought to cease. You feel isolated, adrift in a stillness that seems eternal. This is the universe as we have always imagined it. In its purest state, matter is the exception, and this vast, silent emptiness is the rule. From this vantage point, a galaxy like our own Milky Way appears as a miraculous island of light and complexity, a swirling anomaly in an otherwise barren cosmos. Its 100 billion stars are precious jewels scattered across black velvet. Its nebula, colossal clouds of gas and dust, are the ethereal ghosts of long-dead suns, and the birthing grounds of new ones. Everything we know, everything we are, is confined to these islands. The planets, the moons, the very atoms that form your body were forged in the fiery hearts of these distant stellar furnaces. It's a story of substance, of matter, of something. And for the longest time we believed that was the entire story. A universe of things separated by an infinite expanse of nothing. But now we must challenge that intuition, for it is a relic of a world governed by rules that simply do not apply in the deeper realms of reality. Imagine you are an intelligent creature that has lived its entire life in a single drop of water suspended in the middle of the ocean. To you, the water is everything, the very definition of existence. You might perceive the occasional passing bacterium as a celestial body, a rare and wondrous event. The water itself, however, you would likely dismiss as simple background, the transparent stage for life, not an actor upon it. You would be entirely unaware that this empty water is in fact a seething, chaotic soup of molecules constantly in motion, colliding, vibrating, a universe of hidden activity. Our perception of empty space, it turns out, is much the same. We are the creature in the drop line to the true nature of the medium we inhabit. To see it, to even begin to comprehend it, we must shrink. We must undertake a journey not across the cosmos, but down through the scales of reality, past the realm of atoms beyond the nucleus, into a world so small it defies all logic and all language. This is the quantum realm, and it is here that the concept of nothing is violently dismantled. Here the serene stillness of the void is revealed for what it truly is, a raging, frothing, unpredictable storm of pure potential. The fundamental laws of this universe, it seems, forbid true emptiness. They abhor a perfect vacuum. At the very heart of quantum physics lies a principle of profound uncertainty, a cosmic rule that states you can never know certain pairs of properties perfectly. You cannot, for instance, simultaneously measure a particle's exact position and its exact momentum. The more you know about one, the less you can possibly know about the other. This isn't a limitation of our instruments. It is a fundamental feature of existence itself, and this uncertainty extends to energy and time. The universe, at its most granular level, is constantly uncertain about its own energy state. For infinitesimally brief moments, it can effectively borrow energy from nothing at all, as long as it pays the debt back almost instantaneously. The result of this cosmic loophole, this fundamental jitteriness of reality, is a phenomenon that should be impossible. From the very fabric of space-time particles erupt into being. They are born in pairs matter and its mirror image antimatter, flashing into existence for a fleeting moment, a ghost in the machine of reality. Physicists call them virtual particles. They are not mere theoretical constructs. Their subtle effects have been measured, their existence confirmed in the most precise experiments ever devised by humankind. So now let us return to our silent patch of interstellar space, but this time armed with this new disturbing knowledge. What we once saw as a perfect tranquil void is now transformed. On the smallest of scales, far beyond our ability to see directly, the vacuum is a chaotic cauldron. It is a seething landscape of energy fields fluctuating wildly. It is a quantum foam where particles of every conceivable type boil into and out of existence faster than a flash of lightning. Electrons and their antimatter counterparts, positrons, appear and vanish. Quarks and antiquarks, the building blocks of protons and neutrons, engage in a frantic dance of creation and annihilation. Even photons, the very particles of light, flicker in this phantom realm. This isn't a placid lake. It is a raging ocean, a perpetual storm of becoming and unbecoming. The nothing of empty space is in fact the most dynamic and crowded place in the entire universe. Every cubic centimetre of this void, from the space between your fingers to the vast gulfs between galaxies, is saturated with this activity. It is a background hum, a form of cosmic static, the baseline energy state of the universe itself. This is the energy of the vacuum, and here is where our story takes a turn from the bizarre to the truly cosmic. The theories of quantum mechanics don't just predict that this energy exists, they allow us to calculate, to estimate how much energy should be there. And the number they produce is staggering. It is breathtaking. It is an amount of energy so vast, so colossally, incomprehensibly huge, that it has become the single greatest embarrassment, the most profound puzzle in all of physics. The theoretical energy density of the vacuum is a 1 followed by 120 zeros. It is a number larger than all the atoms in the known universe, by many, many orders of magnitude. If this calculation were correct, the energy locked away in a simple coffee mug of empty space should be enough to boil away all the oceans of all the worlds in the cosmos. The universe should be a violent, explosive place tearing itself apart from the inside out, with a force so great that no star, no galaxy, no atom could ever hope to form. Clearly something is wrong. Our understanding of the universe is split by a chasm a canyon of disagreement 120 orders of magnitude wide. On one side, we have quantum field theory, the most successful scientific framework ever created, predicting this colossal reservoir of power. On the other, we have cosmology, the study of the universe on the larger scales, which tells us that space is for the most part remarkably calm and flat. For decades, most scientists assumed there must be some unknown physical law, some deep cosmic symmetry that cancels this vacuum energy out perfectly. Perhaps the positive energy of one type of virtual particle is perfectly balanced by the negative energy of another, leaving the net energy of the void at a perfect absolute zero. It was a neat solution, an elegant hope for a tidy universe. And for a long time it seemed like the most logical answer. The cosmos looked stable. The galaxies, though moving apart from the initial Big Bang, were expected to be slowing down, pulled back by the relentless grip of their mutual gravity. The universe was coasting its expansion, gradually breaking. But the universe, it seems, delights in shattering our expectations. In the late 1990s, two independent teams of astronomers were engaged in a monumental project to map the history of cosmic expansion. They were using a specific type of stellar explosion, a type Ia supernova, as a standard candle, a beacon of known brightness to measure the distances to the most remote galaxies in the universe. By measuring how much the light from these exploding stars had been stretched and reddened on its journey to Earth, they could calculate how fast the galaxies were receding. Their goal was to measure the precise rate at which the expansion was slowing down. They were trying to weigh the universe to determine if there was enough matter and gravity to eventually halt the expansion and pull everything back together in a big crunch, or if it would expand forever, slowly fading into a cold, dark eternity. What they found was impossible. It was absurd. It was revolutionary. The data coming back from the deepest reaches of space and time was not showing a deceleration at all. The distant supernovae were dimmer and therefore farther away than they should have been. The only way to explain this was if the expansion of the universe was not slowing down under the influence of gravity. It was speeding up. Something was pushing everything apart. Something was acting like a universal anti-gravity. A gentle, persistent pressure embedded in the very fabric of space-time itself. It was a force that was unseeable, untouchable, and yet powerful enough to overwhelm the collective gravity of all the matter in the cosmos. It was a ghost in the cosmic machine, a dark energy whose existence had been completely unanticipated. The discovery was so profound, so paradigm-shifting, that it was awarded the Nobel Prize in Physics, and it threw the deepest questions of cosmology wide open. What was this mysterious force? What was this dark energy? And suddenly, that colossal mistake, that embarrassing number from quantum physics, no longer seemed quite so absurd. Could it be that the two greatest mysteries in science are actually two sides of the same coin? Could the energy of the vacuum, the seething quantum froth that fills all of empty space, be the source of the dark energy that is accelerating the cosmic expansion? The idea is tantalizing. It feels right. It connects the smallest scales of reality with the largest. It suggests that the fate of the entire universe is being dictated by the ghostly dance of virtual particles in the void. But the numbers still don't add up. While the observed cosmic acceleration proves that the vacuum is not perfectly zero, the amount of dark energy we see is minuscule, a whisper of what theory predicts. It is a tiny, delicate positive energy, just enough to gently push the galaxies apart over billions of years. It isn't the universe-destroying bomb predicted by our equations. It is a cosmic thermostat set to a value so bizarrely unnaturally low that it seems to defy all explanation. We have found the ghost, but we do not understand its nature. This is the precipice on which modern physics now stands. We are confronted by a universe that is far stranger than we ever dared to imagine. A universe where empty is not empty, where nothing is a powerhouse of potential, and where an unseen energy born from the quantum fuzziness of reality holds the ultimate fate of all things in its grasp. Is this vacuum energy a constant, unchanging force? The cosmological constant that Einstein once called his biggest blunder? If so, the universe will continue to expand faster and faster until other galaxies are pushed so far away, their light can never reach us, leaving our descendants in a cold, lonely island universe. Or is it something more sinister? Could this energy be changing over time, growing stronger? A phantom energy that will one day become so powerful it will overcome not just the gravity between galaxies, but the gravity holding galaxies together, the forces binding stars and planets, and ultimately the very forces holding atoms themselves intact. A final terrifying end to everything in a big rip. The answers to these questions lie hidden in the nature of the void. They compel us to re-examine the very meaning of space-time and existence. To understand this force, we must journey through the history of a revolutionary idea, from its first conception in the mind of Einstein, to the strange quantum effects measured in our labs and out to the edge of the observable universe. We must confront the greatest numerical discrepancy in all of science, and explore the radical theories attempting to bridge the gap. For locked within the paradox of the vacuum within the energy of emptiness is nothing less than the beginning, the evolution, and the ultimate destiny of our cosmos. The story of nothing is in fact the story of everything. There is a secret hidden in plain sight, an ocean of immeasurable energy, teeming with ghostly apparitions right here in this room, in the air you breathe, and even within the silent absolute zero of your own body. It is an energy that percolates through the deepest, darkest voids between the galaxies, a relentless, shimmering backdrop to all of existence. To find it, you don't need to look up at the dazzling tapestry of the night sky. You need to look into the profound and terrifying idea of nothing at all. For millennia, we believed we understood emptiness. We gave it names like the void, the abyss, the ether. It was the ultimate canvas of cosmic stillness, the silent, featureless stage upon which the grand drama of creation unfolded. The ancient Greeks, in their pursuit of cosmic order, even recoiled from the concept. They imagined a universe so complete, so perfectly full, that a true vacuum was a logical impossibility, a violation of nature itself. Their principle of horror vacui, that nature abhors a vacuum, was not just a scientific observation. It was a philosophical anchor, a belief that the cosmos would rush to fill any emergent emptiness, as if terrified by its own potential for nothingness. This idea held an iron grip on human thought for over 2,000 years, a testament to our innate fear of the void. To our ancestors, space was not an absence but a substance, a transparent, weightless medium called the luminiferous ether, which filled every conceivable crevice of the universe, providing the very fabric through which light itself could travel. It was the invisible ocean for celestial currents, the silent medium for starlight's long journey. The vacuum as a concept of pure unadulterated nothing was a monster lurking at the edges of reason. But then in the 17th century a crack appeared in this ancient edifice of thought. An Italian physicist named Evangelista Torricelli, a student of the great Galileo, conducted a deceptively simple experiment. He filled a long glass tube with mercury, sealed one end, and inverted it into a bowl of the same silvery liquid. The mercury column in the tube fell, but it did not fall completely. It stopped, leaving a space at the top of the sealed tube. A space with nothing in it. No air, no water, no ether. It was the first sustainable man-made vacuum on Earth, a pocket of profound emptiness captured in glass. This small, silent gap, which came to be known as the Torricellian vacuum, was a revolution. It was a direct, tangible refutation of 2 millennia of certainty. It proved that nothingness could in fact exist. With this discovery, the classical view of the cosmos began to crystallize. The universe, as envisioned by Isaac Newton, became a grand clockwork machine, and the stage for this magnificent celestial ballet was space itself, a vast, infinite, and utterly passive void. It was an empty arena, a perfect geometric grid extending in all directions. It did not act, it was merely acted upon. It was cold, silent, and fundamentally dead, the ultimate zero, a perfect backdrop against which the planets would trace their elegant, predictable orbits, and distant stars would shine with unwavering constancy. In this classical universe, emptiness was simple. It was the absence of stuff. If you could remove every atom, every particle of dust, every last stray photon of light from a box, you would be left with a perfect vacuum. You would be left with nothing, absolutely, unequivocally nothing. For centuries, this was the bedrock of physics, the assumed foundation of reality. The void was simply the void, the ultimate state of serene non-existence. But this serene picture, this comfortable certainty of a quiet, empty universe, was destined to be shattered. The dawn of the 20th century brought with it a revolution in thought so profound, it would not just rewrite the laws of physics, it would tear apart the very fabric of our understanding of what it means for something to exist. A new science was being born, a science of the strange, the uncertain, and the paradoxical. A science that would look into Torricelli's silent vacuum and see not an empty stage but a boiling, frenetic, and violent maelstrom of creation and destruction. This was the dawn of quantum mechanics. Quantum mechanics did not arrive as a gentle evolution of old ideas. It was a seismic rupture, a violent break from the predictable clockwork universe of Newton. It revealed a universe that was not solid and certain, but one built on a foundation of probability, chance, and shimmering potentiality. And its most startling revelations would come from looking at the simplest possible question: what happens when nothing is happening? What is the true nature of the lowest possible energy state? In the old classical world, the answer was simple. The lowest energy state was zero. A particle could be brought to a complete standstill. Its energy bled away until it reached a perfect state of rest. But quantum mechanics introduced a new and non-negotiable cosmic law, a principle of profound and inescapable weirdness, the Heisenberg uncertainty principle. Werner Heisenberg's monumental insight was that you cannot know everything about a quantum system at the same time. The more precisely you measure a particle's position, for example, the less precisely you can know its momentum and vice versa. There is a fundamental fuzziness baked into the fabric of reality, a cosmic trade-off that can never be circumvented. But the principle extends beyond just motion and location. It also applies to energy and time. You cannot know the exact energy of a system over an infinitely short period. This simple, almost esoteric rule has a staggering consequence. It means that a point in space can never ever have precisely zero energy. Why? Because to have precisely zero energy, that value would need to remain at zero for a definite period of time. But if you know the energy is exactly zero, the uncertainty principle dictates that your knowledge of the timescale must become infinitely uncertain. The universe at its most fundamental level simply forbids absolute certainty, and that includes the certainty of absolute stillness. There is no perfect rest. There is no perfect zero. This realization gave birth to one of the most mind-bending concepts in all of science: zero-point energy. It is the energy of the ground state of the universe. The lowest possible energy that a system can possess is not nothingness. It is a floor of seething, irreducible quantum activity. Think of it as the universe's own intrinsic hum, a fundamental vibration that can never be silenced. Even at a temperature of absolute zero, where all thermal motion should cease, this quantum trembling persists. The vacuum, therefore, is not a state of placid emptiness. It is the lowest energy state of the universe, and that state is a hotbed of energy. The quiet, dead stage of the classical cosmos was gone, replaced by something far more alive and far more mysterious. So what precisely is this zero-point energy? Where does it come from, and what form does it take? The answer lies in another pillar of modern physics, quantum field theory. This theory tells us that the universe isn't made of tiny solid particles like billiard balls. Instead, it is filled with invisible, intangible constructs called fields. There is an electron field, a photon field, a quark field, a distinct field, for every fundamental particle we know, all permeating every single point in space-time, all overlapping and coexisting. What we perceive as a particle, like an electron, is nothing more than a localized vibration, a concentrated ripple of energy in its corresponding field. It's like striking a bell. The ding you hear is an excitation of the bell's material, and a particle is an excitation of a universal quantum field. But what happens to these fields in a vacuum when there are no particles around? According to classical physics, they should just lie flat, dormant and quiescent with an energy value of zero. Yet as we've seen, Heisenberg's uncertainty principle forbids this. The fields can never be perfectly still. They must constantly fluctuate, constantly tremble, with the universe's inescapable zero-point energy. And here is where reality descends into a kind of beautiful madness. The constant restless simmering of these quantum fields means that energy is perpetually being borrowed from the future. For unimaginably brief moments, a fluctuation in a field can borrow enough energy from the void to create a particle. But this act of cosmic embezzlement comes with a strict rule: the debt must be repaid almost instantly. The more energy that is borrowed, the faster it must be returned. This constant borrowing and repaying of energy from the vacuum doesn't create just one particle. It creates a pair, a particle of matter, and its ghostly twin, a particle of antimatter. For a fleeting ephemeral moment, a fraction of a second, so small it defies human intuition, this pair pops into existence out of sheer nothingness. They are born from the simmering energy of the vacuum itself. Then just as quickly they find each other, and in a silent flash of pure energy, they annihilate, vanishing back into the nothing from whence they came, the cosmic debt repaid. This is the new definition of empty space. It is not a void. It is a quantum foam, a roiling, bubbling soup of these so-called virtual particles, a ceaseless chaotic dance of appearance and disappearance. Everywhere, at all times, even in the most perfect vacuum we can create, the universe is engaged in a frantic ghost rave of particles flashing in and out of reality. This is not some fringe theory or wild speculation. It is a core prediction of our most successful theory of reality. The vacuum is alive. For decades, this astonishing picture of the void remained a purely mathematical construct. It was a bizarre but necessary consequence of the quantum rules, a ghost in the machine of our equations. How could you ever hope to prove it? How do you measure the existence of particles that live and die in less than the blink of an eye? How do you weigh the energy of nothing? It seemed an impossible task, a concept destined to remain in the realm of theory. Until a Dutch physicist named Hendrik Casimir, working at Phillips Research Labs in 1948, stumbled upon a revelation. He wasn't looking for virtual particles or trying to weigh the vacuum. He was investigating something far more mundane, the sticky intermolecular forces known as van der Waals forces, trying to understand why certain industrial colloids behaved the way they did. As he delved into the complex quantum physics, he realized something extraordinary. If this quantum foam of virtual particles was real, it shouldn't just be a passive backdrop. It should be able to exert a real, tangible, measurable force. He devised a brilliant thought experiment. Imagine two perfectly flat, perfectly conductive uncharged metal plates. Now place them in a perfect vacuum parallel to each other and separated by a microscopic distance just a few hundred nanometers apart. According to classical physics, with no electric charge and no gravity to speak of at this scale, nothing should happen. The plates should remain perfectly still, suspended in the silent void. But in the quantum world, the void is not silent. It is a tumultuous ocean of virtual particles of all energies, which means they manifest as waves of all possible wavelengths. Outside the two plates in the vast expanse of the vacuum, there are no restrictions. Virtual particles corresponding to waves of every conceivable length can pop in and out of existence, pushing against the outer surfaces of the plates from all directions. The plates are being bombarded by the full untamed storm of the quantum foam. However, the situation between the two plates is dramatically different. The tiny gap acts as a resonant cavity. It dictates which waves are allowed to exist. Only virtual particle waves that can fit perfectly into the space between the plates, those whose wavelengths are a neat fraction of the distance, can come into being. Any wave that is longer than the gap simply cannot form. It is physically excluded from the space. The result is a profound imbalance. There are more virtual particle waves, more quantum fluctuations pushing on the outside of the plates than there are on the inside. The chaotic storm of the vacuum is stronger on the exterior than it is in the sheltered space between. This imbalance creates a net pressure, a differential in the quantum foam itself. It manifests as a tiny but real force pushing the plates together. A force from nothing, a physical push from an invisible ghostly world. This predicted phenomenon became known as the Casimir effect. It was a prediction of breathtaking audacity. If Casimir was right, then two perfectly neutral objects placed in empty space would be drawn to one another, not by gravity or electromagnetism, but by the very energy of the void itself. The experiment, however, was fantastically difficult to perform. The force was predicted to be incredibly feeble, measurable only at microscopic separations. the plates had to be impossibly smooth and perfectly parallel, as any imperfection would overwhelm the delicate quantum pressure. For nearly 50 years, the effect remained a theoretical curiosity, a tantalizing glimpse into the hidden reality of the vacuum that lay just beyond our experimental grasp. Then, in 1997, physicist Steve Lamoureux at the University of Washington finally devised an experiment with the required sensitivity. Using a delicate torsion pendulum, a device of exquisite precision, he was able to measure the vanishingly small attraction between a gold-coated sphere and a plate. The results were undeniable. The measured force matched Casimir's predictions with stunning accuracy. The whisper from the quantum world had become a shout. The ghosts were real. This was the moment the abstract became concrete. The vacuum was not empty. It was not passive. It is a dynamic and powerful medium, a seething ocean of potential that can reach out and touch our world, that can move objects, that can exert immeasurable force. The classical conception of the silent dead void was officially buried. We had discovered a new kind of energy, one that resides not in matter, not in light, but in the very fabric of space itself. An energy that is present everywhere at all times, underpinning the entirety of the cosmos. But in confirming its existence, we had kicked open the door to one of the most profound and perplexing mysteries in the history of science. This energy is real. It is all around us. The equations of quantum mechanics suggest that if you add up all the zero-point fluctuations, the total energy density of the vacuum should be enormous, staggeringly, cosmically enormous. So where is it? If empty space is truly packed with this much power, why don't we see its effect everywhere? Why hasn't it torn the universe apart? This question brings us to the very edge of our understanding, to the frontier, where the world of the very small, the quantum realm, collides with the world of the very large, the science of cosmology. Because astronomers have found something strange happening on the grandest of scales. They have found that the universe is not just expanding, but that its expansion is accelerating, pushed apart by a mysterious anti-gravitational force. A force they have named dark energy. Could the force driving the cosmos apart be the very same energy we have just discovered in the microscopic gap between two plates? Have we, in trying to understand nothing, stumbled upon the ultimate engine of everything? But this seething energetic quantum foam we've witnessed, this ghostly ballet of particles popping in and out of existence in the smallest pockets of the void, seems a universe away from the grand silent waltz of the galaxies. We have uncovered an astonishing power source, woven into the very fabric of nothingness. Yet the question that haunts us, the question that bridges the infinitesimal with the infinite, remains. Does this microscopic storm have any influence out here across the staggering cold expanses of the cosmos? Can the energy of a near-perfect vacuum, a force born from uncertainty and fleeting existence, actually shape the ultimate destiny of everything we see? To find the answer, we must leave the quantum realm behind for a moment and journey back a century to a time when the universe was believed to be a much simpler, more tranquil place, and to the mind of a single man who, in trying to correct a small imperfection in his masterpiece, accidentally stumbled upon the most profound mystery in science. His name, of course, was Albert Einstein. And in 1915, his theory of general relativity had redrawn the cosmos. No longer was gravity a simple invisible pull between objects. Instead, it was a dynamic geometric property of reality itself. Mass and energy, he showed, warp the very fabric of space-time, and this curvature is what we experience as gravity. His equations were elegant, revolutionary, and they described the dance of planets and the bending of starlight with breathtaking precision. But they held a dark secret, a prediction so disturbing that Einstein himself refused to accept it. According to his own flawless mathematics, the universe could not be static. The immense mutual gravitational pull of all the stars and all the galaxies should be drawing everything together, causing the entire cosmos to collapse under its own weight into a single cataclysmic big crunch. This was anathema to Einstein and to the prevailing scientific and philosophical consensus of the early 20th century. The universe was eternal, unchanging, a perfect and stately clockwork. It had always been, and would always be. A dynamic, collapsing cosmos was not just an unappealing idea. It It felt like a violation of cosmic order. So faced with a conflict between his elegant theory and his conception of reality, Einstein did something he would later regret with every fibre of his being. He altered the theory. He introduced a new term into his pristine equations, a mathematical fix he called the cosmological constant. Represented by the Greek letter lambda, it was a kind of cosmic anti-gravity, a repulsive force inherent to space itself. It was a pressure pushing outward a phantom energy that would perfectly counteract gravity's inward pull, allowing his model of the universe to stand still balanced on a knife's edge for all eternity. It was, by his own admission, a fudge factor, an addition made not from observation or physical principle, but from a desire for aesthetic and philosophical neatness. He imagined this constant as a tiny, unchangeable energy density woven into the vacuum of space. Everywhere you had empty space, you would have this gentle, persistent push. He didn't know what it was or where it came from, but he needed it there to hold his universe together. For a few brief years, his static cosmos propped up by this mysterious lambda seemed plausible. But the universe, it turns out, cares little for our aesthetic preferences. And in 1929, from a lonely mountaintop observatory in California, the American astronomer Edwin Hubble delivered a fatal blow to Einstein's stationary dream. Using the colossal Hooker telescope, Hubble meticulously measured the light from distant galaxies. He was expecting to find a random assortment of motions, some moving toward us, some away. What he found instead was electrifying, a discovery that would forever change our sense of place and time. Nearly every galaxy he observed was rushing away from us. And more shocking still, the farther away a galaxy was, the faster it was receding. The conclusion was inescapable, paradigm-shattering and utterly brilliant. The universe was not static, it was expanding. The very fabric of space-time, the stage upon which all of cosmic history unfolds, was stretching, carrying the galaxies along with it, like raisins in a rising loaf of bread. Hubble's discovery pulled the rug out from under Einstein's carefully balanced model. There was no need for a cosmological constant to prevent a collapse that wasn't happening. The universe wasn't collapsing because it was flying apart, propelled by the leftover momentum of its explosive birth, the Big Bang. Einstein, upon visiting Hubble and seeing the evidence for himself, immediately recognized the implications. His fudge factor, his carefully inserted anti-gravity, was an unnecessary contrivance. He had allowed his intuition to betray his own mathematics, which had been pointing toward a dynamic, evolving cosmos all along. He would later confide to a colleague that the introduction of the cosmological constant was the biggest blunder of his life. And with that, lambda was cast out from physics, a cautionary tale, a ghost of a rejected idea, banished to the footnotes of scientific history. For the next 70 years, cosmology operated under a new, seemingly solid paradigm. The universe was expanding, yes, but that expansion must be slowing down. Every star, every galaxy, every wisp of interstellar dust pulls on every other. Gravity, the great cosmic sculptor, was acting as a universal brake. The only real debate was about the expansion's ultimate fate. Would there be enough matter, and thus enough gravity, to eventually halt the expansion and reverse it, sending everything hurtling back toward a fiery big crunch? Or was the universe's escape velocity too great, destined to expand forever? Its galaxies growing ever more distant, its stars slowly burning out one by one, leaving a cold, dark and empty cosmos in a big freeze. To answer this, astronomers needed to measure the rate of this cosmic deceleration with extreme precision. They needed to look deep into the past to see how fast the universe was expanding billions of years ago compared to today. And to do that, they needed a very special kind of cosmic lighthouse. They needed a standard candle, an object whose intrinsic brightness is so well known that you can calculate its distance just by measuring how dim it appears from Earth. In the 1990s, astronomers found the perfect celestial beacon, a Type Ia supernova. These are not the typical deaths of massive stars. They are the extraordinarily violent and remarkably uniform explosions of white dwarf stars. A white dwarf, the dense remnant of a sun-like star, can only exist below a very specific mass limit. If it's in a binary system, it can siphon material from its companion star. As it gains mass, it approaches that critical limit, a point of no return. Once it crosses that threshold, it triggers a thermonuclear explosion of unimaginable power, an eruption so brilliant it can briefly outshine its entire host galaxy. Because they all explode at precisely the same mass, these supernovae all achieve almost exactly the same peak brightness. They are the universe's own perfectly calibrated light bulbs. By finding these explosions in distant galaxies and measuring their apparent faintness, astronomers could chart the history of cosmic expansion with unprecedented accuracy. Two rival teams of scientists armed with the world's most powerful telescopes embarked on this epic quest. One, the supernova Cosmology project, was led by Saul Perlmutter. The other, the High Z supernova search team, was co-led by Brian Schmidt and Adam Rees. They were competitors racing to be the first to measure the universe's deceleration, and perhaps to decide the fate of everything. They scanned the heavens night after night, searching for these fleeting cataclysmic flashes in the deepest fields of space. Each discovery was a race against time, a mad dash to measure the fading light before it vanished forever. Over several years, they painstakingly gathered data from dozens of these distant explosions. The process was grueling, the analysis complex. They were searching for a tiny subtle effect, the gentle breaking of the entire universe over billions of years. But as the data began to accumulate, a strange and deeply unsettling picture started to emerge. The most distant supernovae, the ones that showed us the universe as it was 5, 6, 7 billion years ago, were consistently inexplicably dimmer than they should have been. This made no sense. For the supernovae to appear dimmer, they had to be farther away than the standard decelerating model of the universe predicted. But how could that be? The only way for them to be farther away was if the expansion of the universe in the distant past was slower than it is today. In other words, the expansion hadn't been slowing down under the pull of gravity. It had been speeding up. The universe was accelerating. Both teams saw the same impossible result in their data. They were terrified. An accelerating universe flew in the face of everything they thought they knew. It required some kind of mysterious repulsive force, pushing space apart, a force strong enough to overwhelm the collective gravity of all the matter in the cosmos. Their first reaction was disbelief. Surely there had to be a mistake. They rechecked every calculation, recalibrated every instrument, reconsidered every assumption. Could interstellar dust be obscuring the light, making the supernovae appear dimmer? They investigated and found no evidence. Could these distant supernovae somehow be intrinsically different from the ones nearby, violating their status as perfect standard candles? They compared their properties and found them to be identical. For months they lived in a state of scientific anxiety, each team trying desperately to find the flaw in their own astonishing result, convinced they were on the brink of either a monumental discovery or a monumental embarrassment. The pressure was immense. Adam Rees recalls waking up in the middle of the night, his mind racing, thinking, "I'm going to be responsible for the craziest result in 100 years of cosmology." But the data refused to yield. The evidence was stubborn, persistent, and pointed in only one direction. Finally, in 1998, after years of painstaking work and agonizing self-doubt, both teams went public. With their results now confirming each other, the conclusion was irrefutable. We live in a runaway universe. Sometime in the last 7 billion years, the familiar grip of gravity lost its cosmic dominance, and a new mysterious anti-gravity force took control, pushing the galaxies apart at an ever-increasing rate. The announcement sent shockwaves through the scientific world. The neatly packaged story of cosmology had been torn apart. The fate of the universe was not the big crunch or the slow big freeze, but a big rip. A future where the expansion becomes so violent it will one day tear apart galaxies, then solar systems, then planets, and ultimately the very atoms you're made of. And to explain this terrifying cosmic acceleration, astronomers were forced to resurrect a ghost from their past. They needed a source for this strange repulsive energy, a force inherent to the vacuum of space-time itself, a force that pushed outward instead of pulling inward. Suddenly, Einstein's biggest blunder didn't look like a blunder at all. It looked like a prophecy. His cosmological constant lambda, the fudge factor he had created to make the universe stand still, was precisely the kind of cosmic anti-gravity needed to make it fly apart. Rescued from the dustbin of history, it was given a new, more evocative name, dark energy. And in that moment, the two great frontiers of physics, the quantum and the cosmic, collided with spectacular force. Because this dark energy, this substance that makes up nearly 70% of the energy density of the entire universe. This force that is dictating the ultimate fate of reality looked suspiciously familiar. A constant, unyielding energy density inherent to the vacuum of empty space, that is precisely the description of the vacuum energy we encountered in the quantum world, the zero-point energy of all those fluctuating fields. For the first time, it seemed we had an identity for this cosmic phantom. Dark energy, the driver of cosmic acceleration, could be the macroscopic universe-scale manifestation of the quantum jitters of empty space. The tiny, fleeting dance of virtual particles when summed up over the vastness of the cosmos creates a pressure that is pushing the universe apart. It was a stunningly beautiful unification, a link between the smallest and largest scales of reality. Einstein's blunder had become his greatest triumph, an accidental prediction of the dominant force in the cosmos, a force born from the very nothingness he had tried to stabilize. But the celebration was short-lived. Because when physicists tried to connect the two ideas mathematically, when they took the tools of quantum field theory and attempted to calculate just how much vacuum energy there should be, they were met with the single, most catastrophic failure of a prediction in the entire history of science. Our best, most tested theory of the quantum world, the Standard Model, provides a way to estimate the energy density of the vacuum. You essentially sum up the zero-point energies of all the known quantum fields. When you perform this calculation, you get a number. It is a precise, unambiguous prediction. Meanwhile, the astronomers, by measuring the rate of cosmic acceleration, had produced an actual observed value for the energy density of dark energy. All that was left to do was to compare the two numbers, the quantum prediction and the cosmic observation. The result was not just wrong. It was incomprehensibly, spectacularly, mind-shatteringly wrong. The value for the vacuum energy predicted by our fundamental theories of quantum mechanics is about 10 to the power of 120 times larger than the value we actually observe in the universe. That's a 1 followed by 120 zeros. To call this a discrepancy is a comical understatement. It is a chasm of failure that tears through the heart of modern physics. It is a number so monumentally, so absurdly wrong that it has no analogy in the human experience. It is like measuring the size of a single proton and predicting it to be larger than the entire observable universe. It's like building a model of the solar system where your theory places Earth somewhere in the Andromeda galaxy. This isn't a small error in need of a slight adjustment. This is a sign that our most fundamental understanding of space-time energy and the vacuum is broken in a profound and terrifying way. This colossal failure is known today as the cosmological constant problem, and it represents the single greatest crisis in fundamental physics. On one hand, we have general relativity, Einstein's theory of gravity, and the very large, which requires a tiny, delicate amount of dark energy to explain our accelerating cosmos. On the other, we have quantum mechanics, our theory of particles, and the very small, which predicts a vacuum energy, so potent, so ferociously powerful, that if it were real, it would have ripped the universe apart in the first fraction of a second of its existence. The stars and galaxies would never have had a chance to form. We would not be here. The fact that we are here, living in a universe that is expanding so gently, tells us that something is dreadfully wrong with our calculations. Somehow, some unknown physical principle or undiscovered symmetry of nature must be cancelling out the gargantuan energy of the quantum vacuum, suppressing it with a precision of 120 decimal places, leaving behind only the tiny residual whisper that we now call dark energy. What is this mysterious cancellation mechanism? Why is the observed value so unnaturally small, yet so perfectly finely tuned to be non-zero? It is a fine-tuning problem of cosmic proportions, as if the universe is balancing on a pinhead one atom wide. We stand at an impasse armed with two theories that are both spectacularly successful in their own domains, yet produce a combined prediction that is an utter catastrophe. The empty space around you, which appears so serene and passive, has become the epicenter of a scientific earthquake, a battleground where our two greatest pillars of knowledge clash, leaving behind a mystery so deep it threatens to invalidate everything we thought we knew about the fundamental nature of reality. And so we stand at the precipice of an intellectual abyss, a chasm so wide and so deep that it threatens to swallow everything we thought we knew about the universe. On one side stands the titanic figure of Albert Einstein, his theory of general relativity sculpting the cosmos on the grandest of scales, bending space-time with the serene elegance of a master artist. On the other side is the frantic, shimmering world of quantum mechanics, the most successful and rigorously tested theory in the history of science governing the subatomic realm with bizarre and unerring precision. For a century, these two great pillars of physics have stood apart, reigning supreme over their separate domains. We always knew that one day they would have to meet, that we would need a single, unified story of reality. But we never imagined their first true confrontation would be a declaration of war. We have asked them a simple question: what is the energy of empty space? And their answers have thrown the whole of science into a state of crisis. General relativity, by observing the gentle accelerating expansion of the universe, gives us a number, an exquisitely small, delicate, almost imperceptible whisper of energy woven into the fabric of space-time itself. The quantum world, however, does not whisper. It screams. Its calculations, derived from the frantic energy of virtual particles popping in and out of existence everywhere, at every moment predict a vacuum energy that is not just larger, but catastrophically, apocalyptically larger. It's a discrepancy so profound that language itself begins to fail. Calling it a mismatch, an error, or a disagreement is like calling a supernova a flicker. The number we are talking about is a 1 followed by 120 zeros, a number so staggeringly colossal it has no physical analogue. If the quantum prediction were correct, the energy packed into a single cubic metre of empty space would be so immense, its gravitational effects would be so overpowering, that the universe as we know it could never have formed. It wouldn't have just collapsed back on itself in an instant. The very concepts of instant and itself would be meaningless. Space-time would be a shredded, boiling, chaotic foam, a tempest of such violence that not a single atom, not a single proton could ever hope to hold itself together for even the most infinitesimal fraction of a second. Imagine trying to build a house in the core of an exploding star. Now multiply that impossibility by a factor greater than all the atoms in the known universe. That is the cosmos, our most successful theory of the small predicts. That is the reality that should be. Yet you are here. We are here. We look out into the silent, majestic darkness and see galaxies drifting with a calmness that borders on the divine. We see a universe that is not only stable, exquisitely balanced, a place where stars can burn for billions of years and life can gain a fragile foothold on a tiny blue world. The universe we inhabit is a flagrant, defiant contradiction to the universe predicted by our own quantum laws. This isn't just a rounding error in a physicist's notebook. This is the single greatest failure of a physical theory in the history of human thought. The chasm between the predicted chaos and the observed calm is the most pressing, the most humbling, and the most terrifying mystery we have ever faced. It suggests that our understanding is not just incomplete, but that it is broken in a way we can barely begin to comprehend. We are staring at a ghost in the machine of reality, a fundamental contradiction that tells us we have missed something enormous, something elemental about the very nature of existence. To truly grasp the horror of this, you must understand that we are not dealing with flimsy speculative ideas. We are dealing with the bedrock of modern civilization. General relativity is not some abstract equation confined to a blackboard. It is a working, breathing part of your daily life. The satellites that provide your global positioning system must constantly account for its effects, for the fact that time itself flows at a slightly different rate for them in orbit than it does for you on the ground. Without Einstein's theory, every GPS in the world would be off by miles within a day. We have seen its predictions come true with breathtaking accuracy, from the gentle bending of starlight around the sun to the violent space-time shaking collision of two black holes a billion light-years away. General relativity is our map of the cosmos, and for a century it has been a flawless guide leading us through the darkness with unerring confidence. It has earned our trust. Its testimony about the universe's gentle expansion and the tiny energy driving it is beyond reproach. It is an impeccable witness, but so is its rival. If general relativity is the architect of the cosmos, Quantum mechanics is the engineer of matter. Every solid-state transistor in every computer, every laser in every fiber optic cable, every medical imaging device in every hospital is a direct product of our mastery over the quantum world. Its predictions about the behavior of particles have been tested to more decimal places than any other scientific principle in history, and they have never, ever been wrong. It is the language of reality at its most fundamental level, describing a world of shimmering probabilities and quantum leaps that defies all our everyday intuition, yet works with the precision of a divine clockwork. When this theory, this titan of predictive power, calculates the energy of the vacuum, it is not guessing. It is applying the same mathematical machinery that allows us to build nuclear reactors and design life-saving drugs. And that machinery produces this number of cosmic annihilation. This is the heart of the crisis. We have two witnesses, both with perfect records, both of whom have revolutionized our world, and they are telling us two completely different stories about the same event. It's as if the world's greatest detective and the world's most advanced forensic lab analysed the same crime scene, and one concluded that a feather had fallen, while the other concluded the entire planet had detonated. The contradiction is so absolute, so fundamental, that it cannot be reconciled by simply tweaking an equation or adding a new variable. This is not a crack in a wall that can be patched over. This is a sign that the entire foundation of our house is built on sand. Something is profoundly wrong. Either general relativity, our theory of gravity and the cosmos, is fundamentally mistaken about how energy shapes space-time, or quantum mechanics. Our theory of matter and forces is fundamentally mistaken about the nature of empty space. Or in the most terrifying possibility of all, they are both wrong, mere shadows of a deeper, stranger reality we have not yet even glimpsed. For decades, the greatest minds in physics have thrown themselves against this problem, and it has broken them. It has resisted every attempt at a solution. The simple answer, you might think, is that there must be some unknown mechanism that cancels out this gargantuan quantum energy. Perhaps there is another field, another type of particle that produces a massive negative energy, precisely balancing the positive energy of the virtual particles we know. It's an attractive idea, a way to restore order and sanity to the cosmos. But for this to work, the cancellation would need to be perfect. Not just almost perfect, but perfect to 1 part in 10 to the power of 120. Imagine two colossal mountains, each trillions upon trillions of miles high, and you're asked to grind them down until they are exactly the same height, with a margin of error smaller than the width of a single atom. Such a feat of cosmic engineering seems not just unlikely, but absurdly conspiratorially so. It would require a degree of fine-tuning so exquisite that it feels less like a law of nature, and more like a deliberate act of cosmic censorship, the universe hiding its own violent truth from us. This problem forces us into a state of profound intellectual humility. We are like ancient cartographers who drew dragons and sea monsters in the blank spaces of their maps. We have reached the edge of our known world, and beyond it lies a vast, uncharted ocean of ignorance. The cosmological constant problem is that ocean. It is the stark numerical proof that our two greatest theories, the twin triumphs of the human intellect, are ultimately incompatible. They cannot both be the final word. This isn't just about finding a new particle or a new force. This is about confronting the possibility that the core principles we have used to build our picture of the universe for the last 100 years, the smooth continuous space-time of Einstein, the discrete quantized energy of the quantum world, are perhaps just approximations of a reality that is fundamentally different from anything we have ever imagined. The problem signals that we are missing a revolution. We are waiting for a new Einstein, a new Bohr to give us a completely new language, a new way of seeing that can finally bridge this impossible divide. What does it mean to live in such a universe? It means that the comfortable, predictable cosmos we thought we were beginning to understand is an illusion. We are adrift in a reality whose most basic property, the energy of nothingness, is a complete and utter mystery to us. The placid silence of the night sky is not a sign of simplicity, but a mask for a deep and violent paradox. The ground beneath our feet, the very stability of matter that makes our existence possible, is a fluke, an exception to a rule of cosmic chaos that our own theories demand. We are the impossible survivors of a shipwreck we were never meant to escape, living on a calm little island in the middle of a raging theoretical storm. The fact that the observed energy of the vacuum is not zero is one mystery. The fact that it is not a monstrously large number is an even greater one. Its value is so strangely, suspiciously perfect. It is just large enough to gently accelerate the expansion of the cosmos, but small enough to have allowed galaxies, stars, and ultimately us to form in the first place. This is the unsettling legacy of the cosmological constant problem. It has transformed the vacuum from a simple empty void into the most mysterious and problematic object in all of physics. It has turned our most cherished theories against each other. And it has forced us to confront the humbling truth that after centuries of brilliant progress of peeling back layer after layer of the cosmic onion, we may have finally reached a point where our intuition fails us completely. The very fabric of reality is not what it seems. We are missing a crucial piece of the puzzle, and until we find it, we are left to wander in the dark armed with broken maps haunted by the ghost in the vacuum. The quiet emptiness of space has found its voice, and it is speaking to us in a language of paradox. It is telling us that our journey has only just begun, and the true nature of the cosmos is wilder, deeper, and stranger than we ever dared to dream. Now the question is no longer just what is this energy, but why? But why? Why this specific, life-permitting, impossibly fine-tuned value? Is it a random accident, or is it a clue, the first hint of a new and revolutionary physics that will forever change our place in the cosmos? The search for that answer is where we must go next into the speculative and exhilarating realm of possible solutions, each more radical than the last. The chasm that opened before us was not merely a gap in our knowledge, it was a fundamental breakdown in the conversation between theory and reality. On one side, our most successful theory of the subatomic world screamed that empty space should be a seething cauldron of energy, a powerhouse so potent it should have ripped the cosmos apart before the first star ever had a chance to ignite. On the other, our observations of the expanding universe revealed a placid, almost imperceptible whisper of energy, a value 120 orders of magnitude smaller. A miscalculation of this magnitude is not a mistake. It is a sign that the very language we are using to describe the universe is profoundly, fundamentally wrong. We had stared into the void, and the void had presented us with the greatest paradox in the history of science. In the face of such a crisis, orthodox thinking shatters. When the trusted maps lead you off a cliff, you have no choice but to abandon them and venture into the wilderness seeking any landmark, any new direction that might lead back to solid ground. What followed was an explosion of intellectual creativity, a period of scientific soul-searching where ideas once relegated to the fringes of philosophy were brought into the stark, unforgiving light of theoretical physics. The search was on not just for a new equation or a missing particle, but for an entirely new conception of reality, a story that could somehow make sense of the deafening silence of the vacuum. This is the story of that search, a journey into the wild, speculative, and sometimes bewildering frontiers of human thought. The most audacious, and to many the most unsettling of these new ideas, does not try to solve the paradox at all. Instead, it embraces it as a clue of a different kind. It suggests that the fine-tuned, life-friendly value of the vacuum energy we observe is not a puzzle to be solved, but a simple fact of our own existence. This is the anthropic principle, a concept that walks a tightrope between profound insight and intellectual surrender. It begins with an undeniable truth: we are here. We exist, we observe, we are made of complex chemistry that requires billions of years of cosmic evolution. And for that to happen, the universe needed to be a very specific kind of place. If the vacuum energy had been even fractionally larger, its repulsive force would have overwhelmed gravity from the very beginning. Space would have expanded so violently that matter could never have clumped together. No galaxies, no stars, no planets, and therefore no one to be puzzled by it. Conversely, if the vacuum energy had been a large negative value, its immense gravitational pull would have caused the newborn universe to collapse back in on itself in a cosmic instant. A big crunch, long before the first atom could even form. So the argument goes, we find ourselves in a universe with a tiny placid vacuum energy for the same reason we find ourselves on a planet with liquid water and a breathable atmosphere. We could not possibly exist anywhere else. This line of reasoning by itself feels like a tautology, a circular argument that explains nothing. but it gains terrifying power when you pair it with another speculative concept from the frontiers of physics, the multiverse. Theories like eternal inflation and string theory do not predict a single universe, but an infinite cosmic foam of them, a vast, ever-branching reality where new universes bubble into existence constantly. In this grander arena, the so-called laws of physics might not be absolute edicts, but more like local bylaws changing from one bubble universe to the next. Imagine a cosmic lottery of unimaginable scale. In each new universe that is born, the value of the vacuum energy is set randomly. In the vast, overwhelming majority of these universes, the number is huge, either positive or negative. These are the failed universes, the stillborn realities, flashing into existence, and then either tearing themselves asunder or instantly imploding. They are sterile, chaotic, and completely devoid of complexity, let alone life. But in an infinite lottery, every possible ticket is eventually drawn. And so by sheer chance, an infinitesimal fraction of these universes will be born with a vacuum energy value that lands in that impossibly narrow, life-permitting sliver right around zero. These are the winning tickets, and of course it is only in one of these extraordinarily rare, finely tuned universes that conscious observers could ever evolve to ask the question, why is our vacuum energy so small? The answer in this view is because all the universes where it wasn't small are silent. There is no one home to notice. This is a breathtaking, vertigo-inducing vision of reality. It recasts our entire cosmos from being the universe to being an island, a tiny, hospitable oasis in an unimaginably vast and hostile cosmic ocean. It suggests that the fine-tuning we perceive is not the work of a master designer, or the result of a deep undiscovered physical law, but merely a selection effect. We are the lucky winners of a cosmic gamble we never even knew we were playing. To its proponents, this is the ultimate Copernican revolution, the final step in removing humanity from any special place in the cosmos. We don't just live on an ordinary planet orbiting an ordinary star in an ordinary galaxy. We may live in an utterly ordinary universe, one of a countless number that just happens to have the right properties for us to be in it. It elegantly sidesteps the calculation problem. The theory that predicts a huge value isn't wrong. It just describes the state of a typical empty universe. We simply don't live in a typical one. Yet for a great many physicists, this is a deeply unsatisfying, even dangerous idea. Science has always progressed by seeking single, predictive, and unique explanations for the phenomena we observe. The anthropic multiverse principle seems to abandon that quest. It replaces a search for fundamental laws with an appeal to infinite chances. Its greatest weakness is its most obvious one. How could we ever test it? How can you falsify a theory that posits the existence of an infinite number of other universes that are by definition causally disconnected from our own? It feels to its critics like giving up. It is a philosophy masquerading as physics, a grand narrative that may be beautiful, but which may forever lie beyond the reach of experiment, leaving us to wonder if we've found the ultimate truth, or simply the most elegant excuse for our own ignorance. For those who find the multiverse too bitter a pill to swallow, another path beckons one that questions a different pillar of our understanding. What if the problem isn't with our theory of quantum fields and the energy of the void? What if the fault lies with our theory of gravity? Einstein's general relativity has been our guide to the cosmos for over a century, passing every test we have thrown at it with flying colours. It is the gravitational script that dictates the dance of planets, stars and galaxies. But perhaps this script has a flaw, a subtle misprint that only becomes apparent when dealing with the universe on the largest possible scales, or with exotic forms of energy like that of the vacuum itself. The theory tells us quite clearly that all energy gravitates. It all contributes to the curvature of space-time. But does it have to be that way? Is it possible that the universe makes a distinction? Perhaps the furious roiling energy of the quantum vacuum, for some unknown reason, simply does not talk to gravity in the same way that matter and radiation do. Maybe space-time is partially deaf to its screams. This would be a radical departure, a fundamental rewriting of Einstein's central idea. It would mean that there is a deep and undiscovered rule in nature's source code, one that effectively shields the geometric fabric of the cosmos from the worst of the vacuum's energetic fury. The challenge, of course, is to formulate such a theory in a way that is mathematically consistent, and doesn't break all the other things general relativity gets so perfectly right, from the orbit of Mercury to the bending of starlight around the Sun. This quest to modify gravity leads down even stranger corridors of thought, into realms that sound like pure science fiction. Some theories inspired by the higher dimensional landscape of string theory propose that our three-dimensional universe is just a membrane or brain, floating in a higher dimensional space called the bulk. In these brain world scenarios, gravity is a strange nomadic force, unique among the forces of nature, and its ability to leak off our brain and travel into these extra dimensions. If this were the case, the immense gravitational effect we expect the vacuum energy to have could be diluted, its power spread thin across a much larger unseen reality. We would only feel a tiny fraction of its true influence, which might neatly explain the gentle cosmic acceleration we observe. It's a tantalizing picture our universe as a leaf on a vast invisible tree, with gravity's roots extending deep into a hidden substrate. These ideas, while mathematically fascinating, are also incredibly difficult to constrain. They often introduce a host of new unobserved fields and parameters that need to be tuned just as finely as the cosmological constant they seek to explain. You risk trading one problem of fine-tuning for another more complicated one. The ghost of the paradox is not so easily exorcised. It often just reappears in a different costume, haunting a new corner of the theory. There is yet a third way, a middle ground between the infinite possibilities of the multiverse and the radical surgery of modifying gravity. This path accepts both quantum theory and general relativity as correct, but proposes that we have mistaken the identity of the culprit responsible for cosmic acceleration. We see something pushing the universe apart, and we have called it vacuum energy, a cosmological constant. But what if it isn't a constant at all? What if the dark energy driving the expansion is not a static property of space itself, but rather a dynamic evolving entity? This idea introduces a new component to the universe, a mysterious invisible substance that has been given the evocative name quintessence. Quintessence, from the ancient Greek term for the fifth element, is envisioned as a new kind of energy field, a gossamer-thin presence that permeates all of space and time. Unlike the cosmological constant, which has a fixed, unchanging energy density, the energy density of a quintessence field can change as the universe evolves. You can picture it as a ball slowly rolling down a very long, shallow hill. In the early universe, the hill was steeper, and the field's energy was higher. Over cosmic time, as the universe expanded and cooled, the ball has rolled into a flatter part of the hill, its energy diminishing to the very small value we observe today. This concept has a number of attractive features. Firstly, it turns the problem from one of fundamental value to one of timing. The question is no longer, why is the vacuum energy so unnaturally small? But, why are we living in the specific cosmic epoch when the energy density of the quintessence field happens to be comparable to the energy density of matter? This is its own puzzle, known as the coincidence problem, but to many physicists it feels like a more tractable one. Secondly, a dynamic field opens up a rich new landscape of possibilities for the future of the cosmos. The fate of the universe is no longer sealed by a single unchangeable constant. If the quintessence field eventually settles at the bottom of its hill, its energy might decay to zero, and the cosmic acceleration could halt. If the hill curves upwards, acceleration could reverse, leading to that ultimate big crunch. And in the most dramatic scenario, if the slope of the hill were to become negative, the field's energy could grow, leading to a runaway repulsive force that would not only push galaxies apart, but would eventually become strong enough to tear galaxies, stars, planets, and even atoms themselves to shreds, in a terrifying end known as the Big Rip. Quintessence transforms dark energy from a static feature of the background into an active, unpredictable player on the cosmic stage. The challenge is that as of now, we have absolutely no evidence that it exists. It is a theoretical ghost, a placeholder for an unknown, invoked to solve a problem but lacking any connection to the rest of our established physics. We have not detected it, nor do we have a compelling theory from which it naturally emerges. It is a compelling story, but one without an author. Finally, we arrive at the most extreme and perhaps most frightening possibility of all. We have questioned our place in the cosmos, we have questioned our theory of gravity, and we have questioned the nature of energy itself. What if the problem lies deeper still? What if the very laws of physics, the fundamental constants we believe are woven into the fabric of reality, are not constant at all? Could it be that values like the speed of light, the charge of an electron, or the gravitational constant itself change over cosmic time? In this view, the cosmological constant problem is an illusion created by our assumption that the rules of the game have always been the same. Perhaps in the fiery crucible of the Big Bang, the physics governing the vacuum was different, allowing for a natural cancellation or evolution that brought the energy down to its present tiny value. This is by far the most radical idea. It means the ground beneath our feet is not solid. It suggests that our entire scientific enterprise, built upon the assumption of immutable laws, might be based on a local temporary snapshot of a much grander evolving legal system for the universe. It is a profoundly unsettling thought, for it would mean that our predictions about the distant past and the far future could be built on a foundation of sand, a multiverse of infinite chances, a new understanding of gravity, a ghostly dynamic field pervading all of space, evolving laws of nature. We find ourselves adrift in a sea of speculation, with each potential shoreline raising as many questions as it answers. We're confronted by a landscape of competing hypotheses, a testament to the raw intellectual power of the human mind, but also a stark reminder of our own limitations. These are not just tweaks to existing theories. They are fundamentally different visions of reality, each painting a vastly different picture of our past, our future, and our ultimate place in the cosmos. The crisis of the void has forced us out of our comfortable home and into the wilderness. And in this wilderness, theory alone can no longer be our guide. The abstract beauty of an equation and the philosophical appeal of an idea are not enough. To find our way forward, to distinguish between the profound and the preposterous, we now have no choice. We must turn back to the universe itself, not with theories, but with telescopes. We must go and look. We need data. We need a new map, one drawn not from the minds of theorists, but from the faint ancient light of the cosmos itself. And so we find ourselves adrift in a profound and unsettling silence. For billions of years, we thought we understood the grand cosmic rulebook. Gravity, the great shepherd of the galaxies, was supposed to be in charge. But the discovery of an accelerating universe has torn that book to shreds. We are confronted with a force, a pressure woven into space-time itself, that is relentlessly and inexorably pushing everything apart. This dark energy, this ghost in the cosmic machine, now dominates our universe, and we are left with the most terrifying question. A sentient species can ask, why? Why this specific amount of energy? Why now? Is it a constant and unchangeable feature of reality? Or is it a slumbering giant whose strength might yet change, unravelling the very fabric of existence as we know it? To stand passive before such a monumental mystery is not in our nature. Humanity does not cower in the dark. We build bigger lights. Across the globe, a monumental undertaking is now in motion, a coordinated multi-generational quest to confront this cosmic enigma head-on. This is the story of our generation's great cathedrals, observatories of unprecedented power, designed not just to see, but to understand. They are our emissaries to the edge of time, our tools for the ultimate autopsy of space. This is the front line, and the offensive is already underway. Our first champion in this new war of understanding is a surveyor of shadows, a cartographer of the unseen. Named after the ancient Greek father of geometry, the European Space Agency's Euclid telescope is tasked with an endeavour of almost unimaginable subtlety and scale. It is not designed to capture the most beautiful portraits of distant galaxies, though its images are breathtaking. Its primary purpose is far more profound: to map the geometry of darkness itself. Euclid is a detective, and its main clue is the oldest light in the universe. As photons from the most remote galaxies journey towards us across billions of years, their paths are not perfectly straight. They are bent, deflected, and distorted by the gravity of everything they pass. They navigate a cosmic ocean whose currents are shaped by mass. Most of this mass, as we've learned, is dark matter, an invisible substance that forms the vast scaffolding upon which galaxies are built. Euclid's genius is to measure the subtle collective distortion of light from over 1 billion galaxies, a phenomenon known as weak gravitational lensing. Imagine looking at a distant forest through a flawed, bumpy piece of glass. The shapes of the trees would be slightly warped. By meticulously analysing those warps, you could reconstruct the bumps in the glass. In the same way, Euclid analyses the warped shapes of countless galaxies to build a map of the invisible glass between us and them, the dark matter. It will create the largest and most accurate 3D map of the universe ever conceived, a ghostly blueprint of the cosmic web's hidden architecture. But how does mapping dark matter tell us about dark energy? Because these two great forces are locked in an internal cosmic struggle. Gravity driven by dark matter and ordinary matter pulls things together. It wants to build structures, to clump gas into stars, to gather stars into galaxies, and to pull galaxies into magnificent clusters. Dark energy does the opposite. It is the anti-gravity pushing everything apart, trying to smooth out the universe, stretching the cosmic web until it tears. The map Euclid is building is not a static picture. It is a history book. By looking at galaxies at different distances, it is looking back to different epochs in time. It will create a series of cosmic maps showing how the clumping of matter has evolved over the past 10 billion years. In the early universe, when everything was closer together, gravity had the upper hand. The maps from that era should show dense, tightly knit structures. But as the universe expanded, dark energy's influence grew stronger. Later maps should reveal that the growth of these cosmic superstructures began to slow down, stifled by the universe's accelerating expansion. By measuring precisely how much that growth has slowed over eons, we can chart the history of dark energy's strength. Has it been a constant, unchanging force since the dawn of time, a true cosmological constant as Einstein first envisioned? Or has its power wavered, growing stronger or weaker through cosmic history? Euclid's map of shadows holds the answer. But this cosmic cartography is only one half of its mission. Euclid has another equally powerful tool in its arsenal, one that listens for the faint residual echoes of the Big Bang itself. In the primordial universe, a mere 380,000 years after the beginning, the cosmos was a seething, opaque plasma of particles and light. This plasma churned with pressure waves, sound waves of unimaginable power, rippling outwards from every point like dropping 1 trillion pebbles into a cosmic pond. These are what astronomers call baryon acoustic oscillations, or BAOs. When the universe finally cooled enough to become transparent, these ripples were frozen in place. They left a subtle imprint on the distribution of matter across the cosmos. Galaxies, it turns out, are ever so slightly more likely to be found at a specific distance from one another, a distance that corresponds to the size of those primordial sound waves when they were flash frozen into reality. This preferred distance, about 500 million light-years across, has been stretched by the expansion of the universe over the last 8 billion years, but it is still there, a faint statistical preference in the clustering of galaxies. It provides us with a standard ruler, an exquisitely calibrated cosmic yardstick. By measuring the apparent size of this ruler at different distances, and therefore at different times in cosmic history, Euclid can chart the expansion history of the universe with breathtaking precision. It's like seeing a 1 meter stick 1 billion light years away, then another 5 billion light years away, and another 10 billion. By comparing their apparent sizes, you can deduce exactly how much space has expanded between those epochs. Combined, the two techniques, weak lensing and BAOs, give us two independent, powerful probes into the nature of the darkness. One measures the history of structure growth, the other measures the history of expansion. If they tell the same story, our confidence in the result will soar. If they disagree, it could signal the existence of new physics, a crack in our understanding of gravity itself. For years, Euclid will stare into the deep, cold dark, patiently measuring the shapes and positions of galaxies by the billion, listening for a faint echo from the beginning of time, all to expose the character of the mysterious force that is currently writing the final chapter of our cosmos. While Euclid charts the darkness with geometric precision, another titan is preparing to join the hunt from the other side of the Atlantic. NASA's Nancy Grace Roman Space Telescope represents a different philosophy of cosmic discovery. If Euclid is a meticulous surveyor, Roman is a grand census taker, a wide-eyed visionary designed to capture the universe in breathtaking panoramas. Its power lies in its sheer, unadulterated field of view. Roman will have the same exquisite sharpness as the Hubble Space Telescope, the instrument that has defined our view of the cosmos for a generation. But it will see a patch of sky 100 times larger in a single snapshot. Where Hubble would give us a keyhole glimpse of a sprawling cosmic city, Roman will deliver the entire cityscape from suburb to shining core in one go. This extraordinary capability will revolutionize the study of dark energy. One of its primary methods will be to conduct the largest, deepest survey of type Ia supernova ever attempted. As we've seen these standard candles, the thermonuclear detonations of white dwarf stars were the very messengers that first alerted us to the existence of dark energy. By measuring their brightness, we can calculate their distance. By measuring their redshift, we can calculate how much the universe has expanded since they exploded. The problem is, these events are incredibly rare and fleeting. Finding enough of them across cosmic history to make precise measurements is a Herculean task. Roman's vast field of view changes the game entirely. It will be a supernova hunting machine without equal discovering thousands of these dying stars in the distant universe. It will repeatedly scan the same enormous patches of sky, watching for the telltale appearance of a new pinprick of light in a galaxy, billions of light years away. With this immense statistical power, Roman will create the most detailed expansion history chart ever conceived, plotting point after painstaking point, each one a star that died to tell us how our universe is growing. This data will allow us to zoom in on the properties of dark energy. We will measure its equation of state, a number that physicists call W, which is essentially a measure of its pushiness. If dark energy is Einstein's cosmological constant, then W must be exactly 1, and it must never change. If Roman's supernova plot reveals that W is 1.1 or 0.9, or if it shows that W was different in the past than it is today, it would shatter the cosmological constant theory. It would mean dark energy is something else entirely, something dynamic and evolving a field that could change its strength in the future, leading to fates far stranger than a simple, quiet expansion. Like Euclid, Roman will also be a master of weak gravitational lensing, mapping the invisible scaffolding of dark matter over vast cosmic scales. Its wide-eyed view is perfect for this work, allowing it to build up enormous maps of the subtle distortions in galaxy shapes far more quickly than any instrument before it. By charting the cosmic tug-of-war between gravity and dark energy over billions of light years and billions of years of history, it will provide a crucial cross-check on the supernova results. It will be a two-pronged assault, attacking the problem from different angles, ensuring that our conclusions are robust and not merely an artifact of one technique. The sheer volume of information Roman will gather is staggering. In its first 5 years, it is expected to generate more data than every previous NASA astrophysics mission combined. We will be deluged with a universe of new information, a torrent of clues streaming down from a point a million miles from Earth. Somewhere buried in that data stream, in the precise brightness of a dying star or the subtle warping of a distant galaxy's light, lies the signature of dark energy, waiting for us to find it, to decode it, and to finally understand the force that holds our ultimate fate in its hands. Yet even these sentinels in space are not alone. Back on Earth, nestled atop a mountain in the Arizona desert, an instrument of a completely different design is already deep into its own quest. This is DESI, the Dark Energy Spectroscopic Instrument. DESI is not an imager, it is a galactic interrogator. Its mission is not to take pictures, but to conduct the largest 3D mapping survey in history by precisely measuring the distance to tens of millions of galaxies. Its heart is a marvel of robotics and optics. At DESI's focal plane, where the light from the Mail telescope is focused, sits a metallic disc, orchestrated by a symphony of microscopic precision. On this disc are 5,000 robotic positioners, each one a tiny automated cylinder that can pivot and move with an accuracy of a few microns. At the tip of each robot is a fiber optic cable, acting as a tiny hungry straw for light. On a clear night, as the telescope points to a new patch of sky, an image of millions of galaxies falls upon the focal plane. In under 2 minutes, a master computer identifies the precise locations of 5,000 chosen targets, and the robots spring to life. They dance across the plate in a whirring, intricate ballet, each one positioning its fiber optic eye directly over a single galaxy, some of them so faint and distant their light has been travelling for over 11 billion years. Once they are locked on, they sit and drink in the ancient photons. Each fiber funnels the light of its assigned galaxy down into one of 10 powerful spectrographs. These machines act like prisms, breaking the faint starlight down into its constituent colours, a rainbow barcode known as a spectrum. And within that spectrum lies the key to the third dimension redshift. As a galaxy recedes from us, carried along by the expansion of space, its light is stretched to longer, redder wavelengths. By measuring the precise shift in familiar spectral lines, the chemical fingerprints of elements like hydrogen and oxygen, DESI can calculate a galaxy's velocity, and from that its distance. Night after night for 5 years, DESI repeats its robotic dance. It will measure the redshifts of over 35 million galaxies and quasars, building a map of the universe of unprecedented scale and detail. This is not a flat two-dimensional projection onto the sky. This is a true three-dimensional model of the cosmic web. We will be able to fly through this map to see the vast voids, the great walls and filaments of galaxies, and the superclusters where they gather like cities of light. DESI's goal is to use this magnificent map to perform the most precise measurement of baryon acoustic oscillations ever attempted. With millions of data points, it can detect that faint 500 million light-year statistical preference in galactic clustering with incredible fidelity across a huge volume of cosmic history. It will track the size of our cosmic standard ruler from the recent universe all the way back to a time when the cosmos was less than a quarter of its current age. This will give us a direct blow-by-blow account of how the expansion rate has changed, allowing us to probe the constancy of dark energy with an entirely new kind of rigor. Euclid Roman and DESI, 3 revolutionary projects each, a masterpiece of human ingenuity. They are our great observatories of the invisible, our cartographers of the cosmic dark age working in concert to triangulate the position of our deepest cosmic foe. They are racing to give us the raw data, the hard observational facts that will finally tell us if dark energy is a simple constant or something far more complex and perhaps far more menacing. But even as these great machines gather light from the dawn of time, another quieter revolution is underway. This one takes place not in the heavens but on blackboards in supercomputer simulations and in the deepest, most abstract recesses of the human mind. For the observational data, no matter how precise, is only one half of the equation. It can tell us what dark energy does, but it can never tell us why it exists. That is a question for the theorists, and it has driven them into the strangest and most wonderful territory imaginable. The sheer absurdity of the cosmological constant problem, that 120 order of magnitude mismatch between theoretical prediction and astronomical observation, has been a declaration of war on our most fundamental physics. It signals that something is profoundly wrong, or at least incomplete in our understanding of the relationship between gravity and the quantum world. The quest for a solution has become a primary driver in the search for a theory of everything. Physicists are wrestling with quantum gravity, the holy grail that would unite Einstein's general relativity with quantum mechanics. Perhaps in the fine-grained probabilistic foam of quantum space-time, new principles emerge that naturally cancel out the enormous vacuum energy, leaving behind just the tiny delicate residue we observe today. Some of the most tantalizing, if controversial, ideas come from string theory. This framework imagines that the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings. For the mathematics of string theory to work, it requires the existence of extraspatial dimensions beyond the 3 we experience. These dimensions might be curled up compactified to a size so small we can never perceive them. In this paradigm, our entire universe could be a 3-dimensional brain, a membrane floating within a higher dimensional space called the bulk. Perhaps the energy of the vacuum is not truly a property of our universe alone. Could it be that energy is leaking off our brain into these extra dimensions, or that interactions with other parallel brains are responsible for the cosmic acceleration we witness? These ideas stretch the very limits of imagination, painting a cosmos far grander and more complex than we ever dared to conceive. And they lead to what is for many scientists the most unsettling possibility of all the multiverse. String theory doesn't predict one unique universe. Its equations allow for a staggering number of possible solutions, perhaps 10, to the power of 500 or even more. Each solution corresponds to a different way the extra dimensions can be curled up, resulting in a different set of physical laws, and a different value for the vacuum energy. Perhaps then our universe is just one bubble in a vast cosmic ocean of other universes, a multiverse, where every possible value for the vacuum energy exists somewhere. In this scenario, we find ourselves in a universe with a small positive vacuum energy, for the simple reason that if it were much larger and negative, the universe would have collapsed back on itself before galaxies could form. If it were much larger and positive, the universe would have expanded so fast that gravity never would have had a chance to pull matter together into stars and planets. Life in those universes would be impossible. So we are here observing this particular value because it is one of the few that allows for observers to exist at all. This is the anthropic principle. It is an explanation that feels deeply unsatisfying to many, swapping a problem of calculation for a philosophical quandary. And yet in the face of a 120 order of magnitude failure of prediction, some physicists are beginning to wonder if it might be the only answer we will ever get. This is the state of the quest, a grand pincer movement on the ultimate cosmic question. From one side, the observers with their robotic eyes and billion-pixel cameras are meticulously gathering the evidence determined to nail down the properties of dark energy with incontrovertible empirical fact. From the other, the theorists are pushing the boundaries of thought, exploring ideas of quantum foam hidden dimensions and parallel worlds, searching for a new framework of reality where the existence of dark energy makes sense. It is a race, a frantic and exhilarating race against the clock of our own understanding. At stake is nothing less than the fundamental nature of space, the fate of the universe, and our final true place within the grand cosmic narrative. The darkness has a story to tell, and for the first time in history we're finally learning how to listen. And so we stand here at the edge of an intellectual abyss, staring into the vast, humbling chasm that separates what we know from what we can only for now imagine. We have journeyed from the quiet certainty of an empty void, a passive stage for the cosmic drama, to this breathtaking and unnerving precipice. We have followed a trail of evidence left by receding galaxies' clues, encoded in the faint ancient light of dying stars, leading us to the most profound paradox in all of science. The vacuum, the very definition of nothingness, is not empty. It is a seething, potent and dominant force, an invisible ocean, whose currents are steadily pushing the entire universe apart. This is the ultimate ghost in the machine of reality, a source of energy so immense it should have torn the cosmos to shreds in the first fractions of a second after the Big Bang. And yet it exists in a state of exquisite improbable balance, a finely tuned whisper when theory screams for a deafening roar. This chasm, this spectacular failure of prediction, is not a sign of defeat. It is the most powerful invitation we have ever received. It tells us that our most successful theories, the twin pillars of 20th century physics, general relativity and quantum mechanics, are incomplete narratives. Einstein's theory, a majestic description of gravity as the curvature of space-time, treats the vacuum as a smooth, placid landscape. Quantum mechanics, our breathtakingly precise guide to the subatomic world, insist that this same landscape is a chaotic froth of virtual particles, a violent, energetic foam of existence and non-existence. For decades, we've used these two languages to describe the universe, speaking one for the very large and the other for the very small. But on the question of the vacuum, they speak at once, and their voices create not harmony but a symphony of profound disagreement. This is where the known world ends. This is the frontier. To confront this mystery is to confront the limits of our own minds, to admit that the architecture of reality is more subtle, more strange and more magnificent than we ever conceived. It forces upon us a necessary humility. We who have mapped the human genome and walked upon another world, who have captured images of black holes and listened to the echoes of creation, find ourselves humbled by the nature of nothing. This quest to understand vacuum energy is therefore not just another scientific problem to be solved. It represents a fundamental turning point in our intellectual evolution, a challenge that demands a new revolution in thought, as profound as the ones initiated by Copernicus, Newton, or Einstein. We are searching for a new language, a unified grammar that can describe the fabric of a quantum space-time, a theory that can finally reconcile the cosmic with the quantum. And our search for this new understanding will not be confined to chalkboards and equations. It is being written in blueprints of steel and silicon in mirrors, polished to atomic perfection, and in detectors designed to capture the faintest whispers from across eternity. We are building a new generation of cosmic cartographers, engines of discovery whose sole purpose is to map the darkness. High in the Chilean Andes, the Vera C. Rubin Observatory is preparing to conduct an unprecedented celestial survey. Night after night for an entire decade, its enormous eye will scan the southern sky, cataloguing billions of galaxies watching for the subtle flicker of distant supernovae. It will create not just a map, but a motion picture of the expanding universe, allowing us to track the history of cosmic acceleration with agonizing precision. By observing how the vacuum's push has changed the clustering of galaxies over cosmic time, we can begin to ask the most crucial question: is this energy truly constant? Or is it a dynamic field, something that has evolved and might yet evolve again in the far future? Far above the distorting haze of Earth's atmosphere, the Euclid Space Telescope is already embarking on its own grand survey. It is a detective designed to see the invisible. Euclid is not just looking at galaxies, it is looking at how the light us from near them has been bent and distorted by the gravity of everything it passed on its journey to us. This phenomenon, known as weak gravitational lensing, allows us to map the distribution of all matter, both the familiar shining kind and the enigmatic dark matter that surrounds it. By charting the growth of these vast cosmic structures, the filaments and voids of the cosmic web, Euclid can measure the cosmic tug-of-war between gravity's pull and the relentless push of the vacuum's energy. It is a painstaking work of cosmic archaeology, sifting through billions of years of history to understand the forces that shaped our universe. Following in its wake will be the Nancy Grace Roman Space Telescope, an observatory with a view 100 times wider than Hubble's. Roman will take the techniques of Euclid and Rubin to an entirely new scale. It will use multiple methods, from mapping the precise locations of galaxies to find the subtle imprint of primordial sound waves known as baryon, acoustic oscillations to discovering thousands of new supernovae in the distant cosmos. Each of these methods provides an independent yardstick for measuring the universe, for taking its pulse across eons. By comparing these measurements, we can search for tiny inconsistencies, cracks in our current cosmological model that could point the way to a deeper theory. It will be a census of the cosmos on a scale never before attempted, providing a data set so vast and rich, it will occupy physicists for generations a new scripture from which to divine the universe's ultimate laws. Even the nascent field of gravitational wave astronomy may hold a key. As we build more sensitive detectors, we may one day be able to listen to the gravitational echoes of the universe's first moments, a time when the properties of the vacuum itself may have been wildly different. These are not just telescopes, they are time machines. They are our eyes and ears on the cosmic ocean, and with them we're no longer just passive observers. We're actively interrogating reality, demanding it give up its secrets. But observation alone cannot solve this puzzle. The answer must also be forged in the fiery crucible of theoretical physics, in the abstract realms of mathematics and pure imagination. Here, in a world built of thought and logic, the search is on for a new paradigm. Some of the boldest minds are exploring the universe of string theory, a radical idea that proposes the fundamental constituents of reality are not point-like particles, but infinitesimally small, vibrating strings of energy. This elegant framework naturally requires more than the three spatial dimensions we experience. These extra dimensions, curled up so tightly they are invisible to us, could hold the key to the vacuum energy problem. In string theory, the properties of our vacuum, including its energy, are determined by the shape and size of these hidden dimensions. The theory doesn't predict a single universe, but a colossal landscape of possibilities, perhaps 10 to the power of 500 or more, each corresponding to a different way. The extra dimensions could be configured each with its own vacuum energy value. This idea leads to a staggering and for some unsettling conclusion: the multiverse. Perhaps our universe, with its bizarrely small and life-permitting vacuum energy, is not unique. Perhaps it is just one bubble in an infinite cosmic foam of other universes, each with different physical laws, different constants, a different vacuum. In this scenario, we find ourselves living in this specific universe. For the same reason we find ourselves on a planet with liquid water, it's one of the few places where the conditions are right for life to emerge. This is the anthropic principle. The idea that our observations of the universe are inevitably biased by the necessity of our own existence. If the vacuum energy were much larger as theory naively predicts, galaxies, stars and planets would never have formed. The universe would be a thin, cold and empty place. The very fact that we are here to ask the question constrains the answer. It's a controversial and philosophically challenging idea, one that pushes the boundaries of what we consider science. How can we ever test for the existence of other universes we can never see or touch? Yet for many physicists, it remains one of the most compelling, if unproven, explanations for our finely tuned reality. Other theorists walk a different path, one that questions the very nature of space-time itself. In frameworks like loop quantum gravity, space is not a smooth continuous sheet as Einstein envisioned. Instead, it is granular, built from discrete, indivisible quantum loops. At the smallest possible scale, the Planck scale space-time dissolves into a network of interconnected nodes. In this picture, the concept of a vacuum is fundamentally different. There is no empty stage. There is only the stage itself, the quantum geometry of reality. Within this framework, theorists hope to find a natural mechanism that cancels out the enormous energies of quantum fluctuations, leaving behind the tiny residual energy we observe today. It is an approach that attempts to solve the problem from the ground up by rewriting the rules of space and time at their most fundamental level. The mathematics are formidable, the concepts abstract, but the goal is nothing less than a complete rethinking of the arena of existence. And there are still other, even more exotic ideas. Could our understanding of gravity be wrong on cosmic scales? Are there new undiscovered fields or particles that permeate the cosmos, whose energy mimics that of the vacuum? Could dark energy be interacting with dark matter in ways we can't yet detect? These questions are driving a renaissance in theoretical cosmology, a period of intense creativity where no idea is too strange to be considered, as long as it can be tested against the flood of new data our telescopes will provide. The conversation between the observer and the theorist, between the data and the idea, has never been more vibrant. It is in the friction between these two worlds, the world of what we see and the world of what we can imagine, that the next great breakthrough will be born. The quest even extends from the cosmic scale right down to the laboratory bench. Here on Earth, experimentalists are pushing the limits of measurement, trying to probe the quantum vacuum directly. In experiments measuring the Casimir effect, they bring two uncharged plates infinitesimally close together in a near-perfect vacuum. The quantum foam outside the plates is more energetic than the foam between them, creating a tiny but measurable pressure that pushes the plates together. It is a direct, tangible manifestation of the vacuum's hidden energy. By refining these measurements with unprecedented accuracy, physicists hope to search for minute deviations from theoretical predictions, deviations that might hint at new physics, extra dimensions, or unknown forces that could be connected to the grander cosmological mystery. Even the world's most powerful particle accelerators, like the Large Hadron Collider, play a role in this story. As they smash particles together at nearly the speed of light, they are recreating the energy conditions of the very early universe. In the debris of these violent collisions, we search for new particles, perhaps the particles that make up dark matter, or even the quantum of a field responsible for dark energy itself, a discovery that would utterly transform our understanding of the void. Ultimately, the problem of vacuum energy is so profound because it sits at the intersection of all the great questions. To solve it is to find the missing piece of a puzzle that connects the birth of the universe in the Big Bang to its ultimate fate in the far future. It requires us to finally construct a theory of quantum gravity, the long-sought theory of everything, that would unite the laws of the cosmos with the laws of the atom. Such a theory would be the ultimate expression of the human intellect, an equation or a set of principles that could describe the universe at its most fundamental level. It would be the final chapter in a story that began thousands of years ago, when our ancestors first looked up at the night sky and wondered not just what it was, but why it was. We began our own journey here with a simple premise to look into empty space. We expected to find a quiet, passive emptiness. Instead, we found the most dominant and mysterious entity in the cosmos. We discovered that the universe is not just expanding, but that its expansion is accelerating, driven by the intrinsic energy of space itself. We learned that nothing is the most powerful something there is. This discovery has reshaped our cosmic narrative. We We now understand that we live in a universe that is not fading out, but is being actively, relentlessly and eternally pushed apart. The future of the cosmos is not one of gentle decline, but of magnificent cold isolation. As galaxies are driven beyond our horizon, their light forever lost to us. This is a universe more dynamic, more powerful and far stranger than any we have ever known, and you are a part of it. The atoms in your body were forged in the hearts of stars that for a time resisted the vacuum's push. The consciousness inside your mind is a product of cosmic evolution, a brief flowering of complexity made possible by a delicate, unexplained balance of cosmic forces. You are a temporary arrangement of stardust living on a small rock in an expanding void, yet you possess the capacity to comprehend that void, to question its nature, and to feel awe at its scale. The search for the secret of vacuum energy is in the end a search for the deepest context of our own existence. It is the next great chapter in the human story, a story of looking into the darkness and finding not an ending but an invitation to begin. The abyss is not empty, it is full of answers waiting for the right questions to be asked, and we have only just learned how to ask.